Hey everybody, and welcome to McArdle Math Academy. In this video we're going to be doing another example of computing work using integration, and this will be the tank type problem. So let's look at the setup example. We have, let's suppose we have a full cylindrically shaped tank as pictured, so I'll show you the picture in a second, of radius 5 feet and height 15 feet, so I didn't write that there, but how much work is needed to pump all of the water from the tank to a point 10 feet above the top of this tank? And what they give you is the density, the weight density of water, which is 62.4 pounds per cubic foot. So let's look at the diagram here to kind of make sense of what's going on. We have this cylindrical tank, it's full of water. We want to pump it to the surface, so imagine if this were underground, 10 feet under the surface. It's got a height of 15 feet, a radius of 5 feet. So before we even start the problem, let's set our reference points here. So I'm going to take the 0 to be the lowest point here. So as we go upwards, we'll be going in the positive direction. Alright, so this is at a height of 15, and this up here would be at a height of 25. And these are all measured in feet. Okay, so in order to find total work, we're going to have to slice up our region. So horizontal slices make a lot of sense here because each horizontal slice of water needs to be brought up the same distance. So we'll draw these little horizontal slices. The beauty of this cylindrical tank is that all the slices are the same size, so we don't have to use any little geometric tricks to find the volume of this slice when we need it down the road. So here's our blue slice. We're going to call this to be a height of y, and we know that the radius of this slice is going to be 5, and it'll always be 5 for all of these slices. Okay, what we want to think about is how much work is required to just bring this little blue slice, and the blue slice has a thickness of dy. So how much work is required to bring just that little blue slice of water from the position it's at to the top? And so you have to think about how far that slice is going to have to travel. And that's what I'll draw in red here. If from the bottom to the blue slice is y and all the way up to the top is 25, then we know that this red distance is 25 minus y. Okay, so let's jump right in and try to find what the work to bring that one slice up to the top is. So we know that work is always given by the equation force, the force that we have to apply to the slice, times the distance that we have to move that slice. Okay. When we're dealing with these problems, force in this case is just going to be the weight of the slice. And the distance, as we just discussed, is 25 minus y, where y is the position, the vertical position of the slice. So now all we have to do is find the weight of the slice. And that brings us back to what I circled in red here, which is the weight density of water. So the density is weight divided by volume. So if we solve for weight, we get that weight is density times volume. And this is what we're going to need as we try to find the work for our given slice. So we'll bring that back down here. This is going to be delta, the density, times the volume of the slice. And all of that is times 25 minus y. Volume of the slice is pretty easy. We come back to the diagram here. It has a radius of 5 and a thickness of dy. So that's really simple. And all of the slices are going to be the same, so it'll be pi times r squared, which is 5 squared, or 25. And then we have the thickness, which is dy. And then you have 25 minus y. Okay, so we clean this up a little bit. We get delta pi times 25 times 25 minus y dy. And that little expression there is how much work is needed just for that slice. Alright, well, in order to find the total work, I'll call that W total, we're going to have to add up the work for each slice. And because each slice is infinitely thin, this adding is essentially an integral. So we have the integral of the work for a given slice, and I pull that right from what we just found here. So we have delta pi okay. And before we start integrating, let's talk about what our bounds are going to be. So let me grab my green color. I need to figure out the bounds of my integration. So we look back to the diagram. The first slice is going to occur right at y equals 0. And then the last slice of water occurs right at y equals 15. So the bounds of our integral become 0 to 15. Okay. And that's it. We just have to do this basic calculus. All of these, delta pi and 25, are all constants. We pull those out of the integral, so we have delta pi times 25. And then all that's left is 25 minus y. So we can integrate that. You get 25y minus y squared over 2. And we go from 0 to 15. Okay. This you'll just use, you'll just input what you need to input there, and remember that delta is 62.4. So I'm going to go ahead and I'm going to find this on my calculator here, and I'll be right back. So we end up with 1.29 times 10 to the 6th, and we just have to think about units. We're working in the British units here, so our work is going to be measured in foot-pounds. And that's our final answer for the total work required to pump all of the water out of this tank. So let me zoom out here so we can get kind of a big picture of what we did. We had our tank, we drew our picture, we figured out what the slice was going to be, and then we found the work just for that little slice. And then we added up the work for all the slices between 0 and 15, because that's where the slices in the tank live, and we found what our final answer was. Alright, hopefully this helps, guys, and I'll see you next time.